Nice. Okay, let's start, I think. Okay, so good morning, everyone. Today I'm going to talk about something new about like j-invariant. Okay, not covering class. Basically, what I want to motivate is the idea of what a j-invariant is and how it is related to elliptic curves and why does it help us to understand the elliptic curve. And in particular, I want to introduce the moduli space of the elliptic curve, which we just say which can be realized as we will see a subset in the complex plane. So the whole thing is very algebraic geometric. I only need a little bit of Riemann surface theory in between, but like because like my reference is Silverman, so AEC is a very algebraic geometric book. But anyways, yeah. So let's start. So the game plan would be look at some things we know about Riemann surface, and then we talk about the J invariant in one lesson before. So I will recover it and like prove an important theorem that we haven't covered about the J invariance, and then we will look at a way to see the moduli space, and then if I have time, I will introduce another definition of the J invariant using hopefully Riemann existence theorem. Okay, so first thing first, we will see an elliptic curve at just a compact Riemann surface of C over a lattice. Okay, so here's the lattice. This is the lattice L, and then we have two vectors, omega 1, omega 2, omega 1. That is the ratio of it. It's linearly independent, so it's the omega 2 over omega 1 is not real. So omega 2 over omega 1, this number tau will be important later on, but for now, we'll just take it as it is. And and it is counterclockwise orientated. Okay, so it is okay. So how to see this as a Riemann surface? We just we just consider this parallelogram, and for every point in the parallelogram, we just choose a unit that's small enough so that it goes into the complex, include in the complex plane. That would be our chart, and then I think there's a technical condition that is like let me see. I think this condition is kind of like the map pi from C to C modulo 2 pi C. Actually no. Yeah. So the normal inclusion, this adds on the Riemann surface C, and then if it satisfies this condition, then it can be put as a Riemann surface structure. And I kind of don't want to do this, but because this is important on the space that H over PSL2C, we will look at later, and it satisfies this technical condition. So I put it here on the slides, but I will just say it here now. Okay, so here's the theorem that we did in class. Is that all elliptic curves can be realized?
Questions on the previous page.
Yeah.
Yes. So the first question is, does the gamma should be finite? So if not be the finite generated group, so could you give a?
So the group gamma.
Yeah, the group gamma is not finite generation.
Yeah. It needs to. Okay, yeah, it needs to be this. So this says that it acts freely on the Riemann surface X, and like in X. In X, the case X, you need this group gamma to be, let me see.
And the gamma is zero, right?
The
gamma Q1, Q2, Q2.
I think this just says that if you have a Riemann surface and you have a group that acts properly discontinuously, and the quotient is also a Riemann surface. It doesn't matter whether finite or not. That's kind of true pretty much for any structure.
But I think in most of the cases you deal with phi like this group subgroup.
But here gamma is here we are applying this to gamma being the lattice.
Yeah, this just you just need this to act freely on on the Riemann surface X. And yes.
This condition here, it's a little bit more than 3D. This is what
Yeah.
properly discontinuous.
Yeah. You need, because it's in neighborhood, not more surface. Anyway, okay. So the theorem we show is that on the Riemann on any lattice C mod L, like using the Abel-Jacobi business, there's actually embedding into CP2 just by considering the Weierstrass rho function, which is defined here. So one thing to note here is that the Weierstrass function in this form depends on the lattice L, which is not very obvious with the notation I choose, but I will continue to use like the Weierstrass P without a subscript L, because and just keep in mind that the Weierstrass P function depends on the lattice L. Okay. Moreover, this embedding is actually an algebraic curve, which can be realized as this polynomial homogenized, because we are talking on CP2. So this is not exactly a polynomial, but you need to homogenize it. And but it is in CP2, C mod L, it is actually an algebraic curve, and we will use this very generously to specify elliptic curve as well. Okay, and in class, the way we show this is that we actually computed G2 and G3 by just saying that, okay, this Weierstrass P is a function with double pole at infinity, and then write out its Laurent expression, and then just choose the correct coefficient such that the terms in the series will Q off each other. And I think with some work you can show that G2 and G3 is the following expression. So what we are going to do is that we are going to change the lattice by a scaling. And obviously, the reason is because we have a theorem that says that two elliptic curves are isomorphic if and only if the lattices are scaling from each other. And we will get, if we just put if we just change L to lambda L, in this case, we will just get G2 to the power will be increased by lambda 4, and G3 will be increased by power of lambda to the power 6. And I use tilde to kind of show that L is changed to the lattice L tilde, where L tilde is gamma lambda L. So that means that the Weierstrass function and the G2 and G3 will change accordingly. So I would denote the new Weierstrass P to be P tilde, G2 tilde, etc. Okay, just keep that in mind. Okay, so taking U, another complex number, to be lambda squared, we will immediately have the following corollary. So two elliptic curves, if they are realized as Riemann-Weierstrass equation, and I have a coordinate change that looks like this, that you remember P is the first coordinate and P derivative is the second coordinate. Okay, second and third actually, because there's a 1 on the CV2. But anyways, if I change it by U squared and U cubed, then they are isomorphic at Riemann surface. And this is because you can, the G2 and G3 are scaled like this, and you have and you can realize the coordinate changes as such. Okay. So here's the approximately a lot of the Riemann surface theory that I need. And now we will look at what the j-invariant actually is. Okay, so recall that the discriminant of a cubic polynomial is this thing. I don't want to derive it. It's Galois theory if it is anything. So in our case, the discriminant will be you just divide the whole equation by 4 and then compute it using this formula. Will be G2 cubed minus 27 G cubed squared. Okay. So our j-invariant, our first definition is introduced as the j-invariant of an elliptic curve C mod L is this expression. So G2 to the power cube divided by the discriminant. So remember that G2 and G3 depends on L. What happens if we scale it? If we scale the L to lambda L, G2, as we just discussed, will increase by a left, or actually divide by, it doesn't really matter here. We'll divide by a factor of lambda to the power 4. So taking to the third power, that is lambda to the power 12. And same here, lambda to the power 12, lambda to the power 12. So I can just take the lambda to the power 12 out, and then that means that the lambda to the power 12 in the denominator and the numerator cancels out, which means that the j-invariant is the same. So indeed, if we change the lattice and the j-invariant is unchanged, that's why it's called invariant. So at least if we have two isomorphic elliptic curves, then the j-invariant is unchanged. Okay, so here's the theorem. It is actually better than that. If I have two elliptic curves, the j-invariant does not change if and only if they are isomorphic elliptic Riemann surface. And secondly, for every remember that like G2 and G3 are just complex numbers, right? They are just like a coefficient of a polynomial, which happens to depend on my lattice L. And the second theorem is that for every number in the complex plane, there is elliptic curve such that J of E is that complex number. So that seems a little bit complicated. Let's put it in even simpler terms. That means J is a bijection from a space M to C, where M is the collection of all elliptic curves. Upon the equivalence condition of Riemann surface isomorphism. So you can see, I think it is not hard to see that these two theorems are actually the same, because and what we are interested is this M, where this M is like M is kind of a geometric object, as it turns out to be, and each point on M corresponds to one elliptic curve, and this will be an interesting thing to look at later on. But for now, let's just look at how to prove this theorem. Okay, so for one, we actually have shown the leftward direction. That is like if they are isomorphic, then the j-invariant isn't changed just by like the scaling argument that we did before. And the second, then we need to do the other direction, which is assume that the j-invariant are the same. So let's just throw out two elliptic curves and assume the j-invariant here are the same. Okay, and then if the j-invariant are the same, then like we just compute the j-invariant and then we get this relation. So and now we are looking for isomorphism of the form of xy equals to u squared x tilde u cube y tilde, because we have said that, okay, if I can see this two elliptic curve as this coordinate change, then it must be isomorphic. Okay, so this is always doable, but I didn't write out the details here, but like here's how you do it. So what relation do we have? We have the relation a cube b tilde square equals to a tilde cube b square, right? And then there are quite a lot of case checking. First, a and b can't be both 0. By the way, if I forgot to mention, if this elliptic curve has this polynomial is always irreducible. So it has 3 distinct roots. Okay, so that means that you can't have both of them simultaneously, a and b or a tilde or b tilde simultaneously 0, or else it will have multiple roots. Okay, so there are several cases to be checked. I will just do one case. Is that suppose a is not 0, and then a is not 0. Let me see. And I think maybe we can just, because I later want to say that there is an isomorphism that goes like taking u equal to a tilde over a. Yeah. 1 over 4. And you can show that like that is indeed the coordinate change plugging on here. And the 1 over 4 here can be any fourth root. There are 4. Of course, a tilde and a are complex, and so any fourth root of this number would work. And there's like another 2 cases, b not 0 and b not 0. I think you also need something here, and then you need a tilde not 0. I think then the book, like in Silverman, they did three such cases, if I recall correctly, and and for each of the cases you have different isomorphisms pertaining to that case. Okay. Okay. So the next part, this is the surjective part of the j-invariant. That's actually very quick. Here's it. Here are three elliptic curves. Here are the j-invariants. So this remember this first case because okay, I didn't put this. Okay, there's a theorem that I assume that I haven't tell you guys is that every elliptic curve can be brought down to the Weierstrass short form that looks like this. And the reason being, you can homogenize this curve and then do a coordinate change for something like y equals to. If I have an elliptic curve that has an xy term in it or have a y term in it, I can do things like y equals to y minus x over 2, and then that kills the xy term, I think, or that kills the y term. I actually forgot which is which, but it is possible. I would just say it as a fact. And okay, here are three curves. And if you change x, do this coordinate change, then you will have a factor, a root of 0 on the right hand side. So in this row, obviously J naught can't be 1728, but it also can't be 0. So this two case does the job. And in any other case, that is a valid elliptic curve, for J to J naught. So these three cases are really distinct. Okay.
So you write it with an xy on the left just to have a simpler polynomial on the right.
Yeah.
Because otherwise, we need to complete the square on the left.
Yeah, you can do it by this coordinate change, basically. Yeah. Which, to be fair, what I plan to do is just put this in Sage and then show that it has the same j-invariant, but I don't find the time to do that. I will just
we'll just add 1/4 on the right if you kill the xy.
Yeah. Okay. So here's the first look of the j-invariant. Now we want to look at M. The thing let's just recall what M is. So M is all elliptic curve on the isomorphism relation, where the isomorphism, E is E tilde if the lattice are scaling apart. So or they are isomorphic elliptic curves. Elliptic curves. We just shown that in class. Okay. So I said that we will look at the quantity omega 2 over omega 1. Let's look at it now. Okay. So omega 2 over omega 1. As I said, it is. So firstly, it is not real because these two need to be linearly independent, and then it always needs to orient in the counterclockwise manner. That means it's on the upper half plane. Okay. Next, we also know that it is obvious that if I take tau equal to omega 2 over omega 1, if I change the lattice by a scaling, so say this is lambda omega 1 and lambda omega 2, then the tau, which now I will call this tau tilde, because I changed the lattice by lambda, and I will call the new lattice tau tilde, then the ratio of this obviously won't change. Okay, so it is really invariant of under isomorphism of elliptic curve. Okay, so for each tau in the upper half plane, at least I can have the okay, no, that's not true. So at least if I found a tau, then it is if I have one tau, then I have all the elements in here can be represented by this tau. So in some sense, this m can be think about as parameterized by the number complex number tau. This is not unique. Here's an example. Okay, so we have this. Let's consider the square lattice. So the square lattice 1 and then I spans the square lattice. But so do. So okay, I should use two different colors, isn't it? So 1 and I, they span the same square lattice. But if I take 1 and I plus 1, they also span the same lattice. Wait, where? Okay. Why? Because I can simply take -1 to be here, right? And then then this point is spanned by 1 and I plus 1. So you can see that they indeed span the same square lattice. But what is a tau in these two cases? Tau in this case would be I plus 1, but tau will just be I in the following situation. So, but they are the same lattice. So for the same elliptic curve, there can be different taus. Now because I just say that tau want to parameterize this space M. I want this tau to be unique. I don't want this to happen. So I want less tau in my space. So not everything in the upper half plane well, this is a bad H. Even worse. Okay, so I want some subset of the upper half plane. I don't want the whole upper half plane, right? Is there a canonical choice of such tau? And so here is the concept of the fundamental domain. Is that okay? I need one more slide. Okay. Without loss of generality, because we are we want to have a canonical choice of tau, so we want to ask whether because we just saw two lattices which are the same can have different tau. We want a choice of tau. So we want to ask when are two lattices with different tau are corresponding to the same lattice, corresponding to actually the same lattice. And without loss of generality, because because we don't care about scaling, and every scaling it must give the same tau, so we can just assume one of the omega 1 to be 1. Okay, so how can different tau be the same lattice? I should not have erased this example, but whatever. So here's my tau. What are the ways that I can change tau so that they span the same lattice? The first way is to take my 1 as it is, and this to tau plus 1, right? And then we saw that because I can just do 1 back, then they give the same lattice. Okay, and in this case, a tau is tau. This case will be tau plus 1. So tau tilde is tau plus 1. There's one of the possibilities. Another possibility is that you actually take this one to be your new omega 1, and then let me see. Yes, you take this to be a net. So you take this to be your new omega 1, and then -1 to be your omega 2. And you can see that it spans the same lattice because again we can flip this, and then that will give you the same lattice. But in this case, what is the new tau? The new tau, because it is oriented counterclockwise, the new tau is -1 over tilde. And you can show, in fact, I give you any basis change of because if I have a lattice, okay. There's a bad lattice. Whatever. If I have a lattice with two linear independent vector, if I have a basis change which might span the same lattice. Given you have a transition matrix that sends like this to this and this to this, right? And this matrix is just a matrix in SL2C. A matrix, a matrix. Wait, I think they're scaling. But okay, my point is every matrix in SL2C, like every such basis change, which does not change. Yeah, you need it to not change the lattice, so it must have determinant one. Because if you have determinant other than one, it will scale up the lattice. I don't want the lattice to be scaled up. I want the lattice to be the same, exact same. So you can show that those two, indeed they give any transformation. So there is a I didn't say the proof. I didn't say the proof here, but there's not a hard proof. This can be realized as the matrix 1, 1, 0, 1, and then this will be 1, 0, -1, 0. If I wait, no, 1, right? So this, I think you call this matrix S, and then you call this matrix T. Oh, it is. It's kind of. Let's just do this again. So 1, 1, 0, 1, and 1, 1, 1, 0, then 1, 1. I think, and I think you have an action from tau to A tau plus B over C tau plus B, and it is given by those two matrices. Yes. Okay. Okay. So and then you can show that these two matrices generate SL2C. It is a very good theory proof, so I don't really want to cover it. But essentially, what you did, you have your matrix in SL2C. You keep doing division algorithm until one is minimal, and then you just applying you just apply this matrix until you get all the things into the identity. Okay. So, but what I want to do is to give a very geometric proof of what I just said just now, without using all this madness. And it's a proof by I think I heard this from Professor Bolcher's YouTube video, and I found it really, really cool. Okay, so let's look at the question again. What is the question again? So this kind of okay. So what I want to do now is present a geometric proof of this thing and actually seeing the space M. Okay. So we want this lattice to be the same, right? So we want a canonical choice of this tau because as I repeated again, this tau can be different while the lattice being the same. So what are the choice for tau? The choice for if I look at omega 1 and omega 2, then I kind of want if I want a canonical choice of a somehow unique choice of such a basis, let's just assume this is the shortest. So if that means if I assume I said without loss of generality, I assume this is 1, then the modulus of this must be larger than 1. Then we don't this is one of the criteria of the unique choice, okay?
Would be equal to 1? The absolute value.
Yes. You have the square, which is equal to 1. Yeah. So larger than or equal to 1, my bad. Okay.
So as 1, you choose the shortest non-zero vector in the lattice, right?
Yes. And then I scale it down. So I didn't scale it down.
I scale to make that one.
I scale to make that one. Yes. Okay. So that means that I must lie on top of this circle. Next, here's a very nice idea. Is that if I have another vector that represent this space, that represent this lattice, so let's just say they represent the same lattice, I can always bring down by a vector of 1, right? because like 1 is in here, and I can always bring down 1. And same if I have something here, I can just, if I have something on the left, I can bring down my +1. So the distance between this omega 2 that I want, or this tau that I want, is actually not omega 2 because I scale it to 1 already. So there is tau, and it should be large. So it could, because I can bring it down, and that will give me the same lattice, I actually want the distance between tau and 1 not greater than 1. So the distance of tau and -1 and the distance of tau and 1 is actually less than 1. That means this region is the tau that we are looking for. With some caveat, I need to tell you now. We just say that we need to identify tau and because if tau, we just say that we have tau to tau +1 and tau to -1 tau, right? So like this is not open nor closed because we need to identify this thing with here. You can see that the transformation is literally tau to tau +1 if I identify this thing with this thing. And we want to identify this arc as well. This is tau to -1/tau. Because you can see, let's say in this thing, it corresponds to a lattice that looks like, okay, maybe let's say this one, right? It just corresponds to a lattice that looks like this. So like you can choose this vector and this vector, it will represent the same lattice. So we kind of need to do the identification between the two sides here and the two arcs here.
Could I ask you a question? So the first vector that you'll call 1 eventually, you just choose as the shortest vector.
Yes.
So, and since it's the shortest,
it will like the next vector, because I want to parameterize this.
That means that any other is outside of the circle.
Yes.
And then the other one you just, well, you declare that 1, so now any other vector has absolute value greater than 1, and then you just choose the one that has the real part between -1/2 and 1/2.
I need to choose I need to choose the spanning vector, and then I can choose in a way such, because if I choose a vector, a spanning vector, if I choose a spanning vector that is have the real part larger than 1/2, then I can just bring it back by by this vector, right or the left. So like it must lie between those. It must lie.
Yeah, because a priori it would seem that if you have something outside of this half disk, when you start bringing it back, it may get inside the disk. But I guess that's not possible by your.
No, because not possible. Because let me see. Appeal. Well, it's possible, but we just like if we because.
But that would mean that we didn't choose the shortest there.
Yeah. If like it, yeah. And like if we go, let me see. Yeah. That would be like if I can bring it inside inside this, then that would be the shortest, and I can just scale that to become my 1. Right. Okay. So and like here's another picture, and and.
So what you proved is that you can always choose tau in that gray domain.
Yes.
Or its closure.
Yes, and it is even better. Is that like because tau is just elliptic, like it's just elliptic curve, right? So each point in tau represents one elliptic curve, and 2 different points are different. So those 2 points, they are indeed not isomorphic. So I actually found a nice animation online. See, like you, each point in the each point is like the all the way you want to think about it is like each point is the orbit. It's like this to this is tau to tau minus one, this to this is tau to negative one over tau, and like each of the point here like represent the same elliptic curve. So each point of here, like although the taus are different, they represent the same lattice of the sphere, and and you can move this around, and that correspond to different elliptic curves. Okay. Okay.
You have just a few minutes left, so maybe let's
Yeah.
get some conclusion.
Yeah. No. I guess I will. I guess I will conclude on here, and maybe. Yeah. Like the conclusion is that like the J function is actually bijective. It sense because now we have a geometric description of M, and then we show that M is this thing. So J sends this thing to a complex number, and it satisfies the following relation for A, B, C, D in SL2C. And like this is important because it's a modular form, and this extends to a function on on the upper half plane because as the animation just showed, like you can kind of extend this to the upper half plane. So each of them is a copy of so the upper half plane can be tiled in the sense that like by the transformation using those two transformation at this region. So
what do you call the fundamental domain? Is it open region or closed region?
yeah, like the thing is like different textbook have different thing. Like because in modular forms, what you want to do, like if you identify these two sides and these two sides, that will give you a sphere without a point, right? And then like usually in like if I look at modular textbook, they will have one extra point called I infinity just to close up the sphere. But like in this context, because it is like we don't want to have this extra point because like we have a bijective function from this region to C. So it is not open or closed. It is something that looks like this because like this is we need those, but we don't need we need this half, but we don't need this half because it is identified by those. So yeah, so that is my fun. But I think some folk the definition of the fundamental domain is such that the closure, like if I close, like it's the closure of the set satisfying this property. So like it is over the place. And I think and the thing that I didn't have time to prove is actually to show that this is a holomorphic function from that to complex number. But then if we put a Riemann surface like structure on this space, which just goes very back to this requirement that we have, which end up like this region satisfied, and this is H, and the group is PSL2C, and then we have a Riemann surface, and then that will be my isomorphism. Yeah. So I guess that's all I want to do for now. Thank you so much.
Thank you. Any questions? Yeah, with the shortest vector, it's definitely a better proof than what the textbook does.
Yeah, I really like that proof. Like, and I mean, there's like the way I learned it at first is the algebraic proof of this generic SL2C, and then that follows. But like, you need to show that the region is this one, which like yeah, the textbook did a way of like choosing this. But I think like the textbook needs to do the way about choosing a this because it also want to show that you want to put a Riemann surface structure on this thing because like a priori you don't have Riemann surface structure on here. But I'm not sure. Okay.
Can I ask?
Yes.
I don't immediately see why. I see why the left boundary of that strip is identified with the right, but I don't quite understand why the left like sub arc.
The arc, right?
Yeah.
Let me see. Okay, so here's an intuitive like.
I think through -1 over 2.
Here's a very there's an intuitive explanation that I learned is that this point, right, corresponds to, let's say this one corresponds to this. And then like what you can do, as I said, is to take this as your omega 1 and then this as your omega 2.
Right, yes.
And then that will give you the same lattice and that corresponds to this change.
Yeah, it's exactly that.
Negative 1 over 0 on a circle.
Right. Right. Okay. Okay. Thank you so much.
Thank you.